Okay, hello everyone. Today we have a pleasure to have Marwan El-Idrissi with us. Marwan is a postdoc, a recent postdoc in University of Quebec, Montreal. Please correct me if I'm pronouncing anything wrong. But the important thing is that he just got his PhD in France on applied mathematics, working on theoretical developments in global sensitivity analysis. And this is what we came here to listen to. Maran, the floor is yours. Go ahead.
Well, thank you very much, Maria, and thank you so much for this opportunity to present some parts of the work that we did during my PhD. So yeah, I wanted to share some things with you, some ideas that we had, and some start of answers to some questions when dealing with dependent inputs. And in particular today, what I wanted to share with you, we're going to talk about Sobol indices, Shapley effects, and a new path towards trying to handle dependent inputs, which is a really complicated question. So this work has been done during my PhD. It was at EDF. So EDF is France's main electricity provider and producer as well, but also in l'Institut de Mathématiques de Toulouse. And this is the work that we did conjointly with my supervisors, which were Nicolas Bousquet, Fabrice Gamboa, Bertrand Yos, and Jean-Michel Loubès. And the first slide is a presentation slide, in the sense that I wanted to talk a bit more about who I am and what my interests are. So yes, I did my PhD. I actually defended my thesis last March. And it was on the subject on trying to develop new interpretability methods to try to certify machine learning models whenever they're applied to critical systems. And now I'm a postdoctoral researcher. It's been a month and it's been doing great in Montreal at Université du Québec à Montréal. And I'm supervised by Arthur Charpentier, but also Marie-Pierre Côté from l'Université de Laval. And I'll be working on mainly the same thing, but applied to actuarial sciences, and in particular with a focus on trying to assess the fairness of black box models and a bit of causal inference as well. So here I'm a very curious person, so there's a lot of topics of interest, but actually most of them are related to probability, uncertainty quantification, and sensitivity analysis, since I'm from this community. So a bit of context. Being able to understand how a black box model behaves under uncertainty is crucial if we want to use them, and mainly AI models, for critical systems. So what I mean by critical system are industrial processes, energy production, medicine, cars, planes, the stock market, basically something that can have an impact, which can be, for example, on human lives, but which isn't a problem of trying to spot a cat on a picture, for instance, something a bit more complex with real consequences. And usually, when we're dealing with critical systems, the decision-making process must be justifiable and justified, in the sense that going and talking with safety or regulation authorities by saying, yay, my model is state-of-the-art because it works well on this and this and this benchmark, is usually not enough to be able to convince them to use them, for instance, in an electoral like a dam to produce electricity. Because if it goes wrong, you need to be able to know why it goes wrong. And this is why we must turn to theoretical arguments, because proving, for instance, that my model behaves the way it should has a lot more power than just checking that it works on some limited set of benchmarks. But what we found is that some of the theoretical developments often rely on unrealistic assumptions. When I say unrealistic is with respect to the reality, meaning that mutual independence, for instance, of the inputs when working on an XAI, explainable AI setting, is not really realistic because a lot of data sets actually show a behavior of inputs being correlated, at best, linearly correlated, but non-linearly correlated as well. And So the question is, how can we go beyond this mutually independent assumption on the inputs? So in this talk, we are not going to talk about estimators. I'm not going to talk about particular methods to compute some indices or some effects or to compute the importance of some inputs. We're going to focus on what we're trying to achieve, trying to find the right metric, and the estimator is going to come next. And what we're going to do is to explore the behavior of the theoretical quantities and whatever happens whenever the inputs become dependent between one another. So a quick outline, we're going to start from Hoeffding's decomposition to the Sobol indices. I'm pretty sure all of you know what I'm going to talk about. Then we're going to talk about the Shapley effects and the cooperative game solution. And then at the end, I'm going to open with some really recent work that we did to try to disentangle what we kind of mean by an interaction and the dependence, the effects of an interaction induced by the model, and the effect due to the dependence between inputs. Because these can be different things, but the disentangling them is actually pretty hard. So, starting a bit of mathematics, I try to keep it really, really vulgarized. But here, D is going to be the set of 1 to D. I'm going to have D inputs. My inputs are going to be D variates. And P of D is going to be the power set of D. So all the subsets of D. So for example, yeah, if I have 2 inputs, D is going to be the set 1 and 2. And the power set of D is going to contain the empty set, 1 by itself, 2 by itself, and 1, 2 together. Okay, so it's going to have 2 to the power of D elements, small d elements. X is going to be a random vector of mutually independent inputs at first. And then XA is going to be a subset of the input. So it's also going to be a vector, but with less inputs, basically. And here G is a given black box model such that its variance, when applied to X, is less than the infinity. Basically, it's square integrable. So amazing result from the 50s. Hoeffding showed that you can actually uniquely write any model, any random output G of X as a particular sum of what I'm going to call representants, which are going to be in blue, of, in a sense, increasing dimensionality. Essentially, what it states is that, for example, a bivariate function G of x1, x2 can be written as a constant plus a function of just x1, a function of just x2, and a purely bivariate function of x1 and x2. And so he showed that you can write this whenever the representants are all pairwise orthogonal. Take any 2 of them, compute the correlation, look at the correlation, it must be equal to 0. So this is somewhat of a constraint. And moreover, we not only know that we can do this, we can characterize these representants by using this weird green sum, the sum of the -1. It's going to come in handy after, multiplied by a conditional expectation. So this is great. If we were able to compute all of these conditional expectations, then we would have a direct access to the representants. And the representants, they can be interpreted as interactions induced by the model G. And this is really great for post-hoc interpretability purposes. For instance, if I'm taking this really simple example where here my inputs are a Gaussian vector and they're mutually independent, and my model is really simple. It's x1 plus x2 times x3. What I have is that the representant G1 of x1 is actually equal to x1, and the representant G23 of the interaction between x2 and x3 is equal to x2 times x3. And all the other ones are equal to 0. So by using the conditional expectations, I can actually gather this decomposition without even knowing what G of X is. This is why I'm talking about black box inputs. And that's what I just said. So But more generally, in global sensitivity analysis, what we want to do is to quantify what I'm going to call the importance of a set of input. And what I mean by the importance is that an input is going to be important if it contributes to the model's uncertainty. And the amount of uncertainty in the model or in the system that I'm modeling is actually the variance of this system. Meaning that if the variance is high, the uncertainty is high. And a solution to be able to quantify the importance is to decompose the variance of G over X with respect to the subset of inputs. And actually, this is what Sobol and what the Sobol indices are, is just leveraging this orthogonality condition to be able to decompose the variance of G of X directly with respect to the variance of the representatives. And this works because everyone's orthogonal with everyone. There's no covariance terms, basically. And in this case, the model's uncertainty is actually equal to the sum of its representants' uncertainty. So I'm able to say, yeah, most part of the system's variance is due to this particular interaction of this particular input. And this is amazing. This is an amazing tool. And they're always positive, which is great. And they sum to 1, which means that they can be directly interpreted as a percentage of the model's overall uncertainty. But they actually require the inputs to be mutually independent. And we can see this because if we keep the same formula with the conditional expectations for the Sobol indices, but in this case, I'm going to add some linear correlation between x3 and x1. Whenever rho is equal to 0, so this is the mutually independent case, what I see here is that half of my model's uncertainty is due to x1, which makes sense. And the other half is due to the interaction between 2 and 3. And it makes sense. But in the correlated case, I have these extra terms, which can be negative, which is really weird in a sense, because a negative percentage it's hard to interpret. And they're in some arbitrary places, because here, if I were just to look at this, if I didn't know my model and were just to look at these results, I wouldn't know. Maybe there's an interaction between the 3 inputs, because I'm seeing a number here. It's not 0, but I'm not able to really truly interpret what my model is, basically. So their overall interpretation as pure interaction effects, it doesn't hold anymore. And this is really the case where I keep the same formula and I still compute the Sobol indices, even though they're not mutually independent. So there's 2 problems. The first one is that the effects can be negative due to the dependence. And the second one is the unclear interpretation, because we're not exactly in the situation of Hoeffding's decomposition. But there are solutions, and actually 2 of them. The first one, to solve the negative effects, we can use cooperative game theory. And for the second one, I'll try to show how to go a bit beyond Hoeffding's original decomposition. So I'm going to start with the cooperative game theory spiel, with going directly into what are the Shapley effects. It's just an egalitarian redistribution of the Sobol indices. It's just that. And what I mean by an egalitarian redistribution of the Sobol indices is that the recipe is you first compute the Sobol indices, even if the inputs are dependent. So you have negative values. Then you're gonna you're gonna grant XA with the value SA over the cardinal of A. What it means is that, for example, I'm gonna give to X1 its individual Sobol index, then the interaction with 1, 2 divided by 2, and if there's 3 inputs, the interaction between 1 and 3 divided by 2 as well. And then for the third order interactions, I'm going to divide them by 3 and give 1/3 to X1, and 1/3 to X2, and 1/3 to X3. This is the egalitarian part. And that's it. So these are just what the Shapley effects are. And we can actually write them in a nice little formula. And actually, these are always non-negative, even if the Sobol indices can be negative. These indices, the Shapley effects, they're always non-negative, and they sum to 1. So they can also be interpreted as a percentage of variance. But here, I have d of them, whereas the Sobol indices, I had 2 to the power d of them. But okay, we know how the Shapley effects were, but let's take a step back and go into the more general framework of what cooperative game theory is. So the Shapley effects are derived from the Shapley values, which stems from cooperative game theory. And if I wanted to explain really simply what cooperative game theory is, just the art of cutting a cake. How can we cut cakes, basically? So the theoretical setting looks a lot like what I just did before. So I have D, and which is going to represent a set of players instead of a set of inputs. And P of D is going to be a set of coalitions of players. And here I'm going to have V, which is a chosen value function. I'm going to choose D. I have full control over what this value function can be. And the set DV formally defines what's known as a cooperative game. And the main question is how to redistribute V of all the players, the value produced by all the players together, the cake, into small d parts among all of the players. And how do we do this? It's by using what's known as an allocation. And an allocation associates a share of the cake to inputs individually. So it's a mapping which takes an input, an individual input, not a coalition, an individual input, and returns something in R, a value, a real value. And for importance quantifications, we have 2 criteria. The first one is efficiency. Efficiency is just the sum of the effects, the sum of the allocation must be equal to the cake. And the second one is non-negativity, which is just that all the shares of the cake must be positive. In a sense, I'm not allowed to make like a credit cake or a loan of a cake. And we can understand these 2 criteria as to redistribute the whole cake and nothing but the cake, basically. And if these criteria are respected, we can actually interpret the allocation as the percentage of the variance allocated to an input. So the question becomes, how can I define efficient and non-negative allocations? And we can do this in a particular way by using the notion of Harsanyi dividends. So Harsanyi dividends are just defined as being, so they're in blue, this is not a coincidence, as being this green sum, this is the same one as before with the Sobol indices, multiplied by this red value function that I've chosen. And it's just a mapping, so there's 2 to the power of d of them. I give them a coalition of players and it returns a real value. And they can be interpreted as the added value produced by each coalition. And the thing is, they always sum up to V of D. Sure looks a lot like Sobol indices, right? And from these dividends, I can define a set of allocations which are just aggregation of the Harsanyi dividends. Basically, what I'm saying is I'm going to make the sum of the dividends, and I'm going to put a weight in front of them with some weight that must respect some constraints which are not too restrictive. And the nice thing is that allocations defined like this are always efficient, and they're non-negative is V if V is monotonic. But this is the case for the variance of the conditional expectation. It's a monotonic function with respect to A. And the Shapley values are just the egalitarian redistribution of the dividends. So it's just the sum of the dividends divided by the cardinal of A, just like as we've seen before with the Sobol indices. And the idea is that from the values, I'm going to compute the Harsanyi dividends, which can be interpreted like this with 3 inputs. The dividend is actually going to be, the dividend of 1 is actually just going to be this this part here, and the dividend of 1, 2 is going to be this interaction between them, the thing that they have in common. And the Shapley values are just like cutting it in half, giving half to 1, half to 2. And for 3 inputs, 3 players, it's 1/3 to each and every one of them. And this is actually what Owen did in 2014 was actually focus on one particular game where the value function is the variance of the conditional expectations, which are more or less, I've forgotten a normalizing factor here, but the closed Sobol indices, which act as a value function. And the Sobol indices, actually, by using the green sum, the sum of the -1, we actually retrieve the Arseny dividends, which are equal to the Sobol indices. Even if there is dependence, it amounts to computing the Sobol indices whenever the inputs are dependent. But the Shapley effects have a practical drawback. And this drawback, we called it Shapley's joke, is that an exogenous input can have a non-zero share of importance. For instance, here with the, again, really simple model, x1 plus x2, but I have a third exogenous input, which isn't in my model, but is correlated with x1. And in this case, we can see that its Shapley effect can actually be positive. It can be not equal to 0. And this can be a problem for screening, for instance, where you're trying to see if some input does actually have an influence, a direct influence due to an interaction in a model, but your inputs are also dependent. And to solve this issue, what we did was to just take a different redistribution. So the Shapley effects are an egalitarian redistribution, but we studied the proportional redistribution. It's proportional in a fairly complicated manner, but it led to the definition that's just changing the way that we aggregate the Sobol indices to the proportional marginal effects. And we did this work with Margot, which at the time was an intern at EDF. And now she's doing a PhD on some really complicated stuff dealing with Choquet integrals. And she's really smart and really good at mathematics. And actually what we managed to show is that under really mild assumption on the probabilistic structure of X, the proportional marginal effect of an input I is equal to 0 is actually equivalent to this input being exogenous. And when I say mild assumptions, and here I'm not saying that the inputs must be mutually independent. It's like technical stuff by stating that I can't express a set of inputs as a function of another set of inputs, basically. It's like multicollinearity, but the nonlinear version of it. And in practice, what we saw is that they tend to discriminate more than the Shapley values when the inputs are highly correlated. Because if the inputs are highly correlated, the Shapley value, since it's egalitarian, is going to give the same importance to everyone. Basically, more or less the same importance. Whereas here, it's a bit more discriminative. And to show this, so yeah, first I lied when I said that I wasn't going to talk about the estimators. I'm just really quickly going to talk about challenges with estimating either the proportional marginal effects or the Shapley effects. Because whenever you're trying to estimate the value function for every correlation possible, this means computing the closed Sobol indices for every set of inputs that you can. So basically, you need to compute 2 to the power of d things. So if you add an input, if the complexity of your model scales by 1, it's going to be exponentially more costly to compute them. And there's basically 2 settings. The one is if you can sample your model at will and you're able to actually simulate your inputs with respect to all the possible conditional laws. In this case, you can use a Monte Carlo scheme to be able to estimate the proportional marginal effects and the Shapley effects. But there's also a given data setting where you only have access to an IID sample, and we can use a nearest neighbor procedure, which still requires 2 to the power of d estimates, but we can actually estimate them from a single data set. So these methods are really time consuming and they scale exponentially with the number of inputs. But if I commit to estimate the Shapley effects, I can actually recycle the same estimates to compute the proportional marginal effects, because the only differing thing is the way that I aggregate these values. And there's a lot of many really smart strategies to drive the computational burden down, but it's going to be at the expense of the precision. But there's a lot of work by a lot of really smart people to make computing these effects actually a reality. So quick little example. So here I have a model which computes the transmittance performance of an optical filter. So I have an optical filter. There are 13 different consecutive layers in them. The idea is that I put some light at the beginning. The light is going to scatter through the field to the layers and then regroup at the output of the filter, and I'm computing the amount of light, basically. I'm not an optics expert, so the amount of light at the start and the amount of light that goes through the filter, and I'm computing the difference between the two. And this is an idea of the performance of a filter. Here, my inputs, I have 13 of them, and they're going to be the refractive index error of each of the layer. If there's a defect, for example, on layer 2, I2 is going to be how much of a defect it is. And here, these errors are highly correlated, and we've put this correlation because we can think of the manufacturing process. Maybe they're made in sequence, and if the first one has a defect, then it's more likely that the second one is going to have a defect as well, because they made them sequentially. And this model, so it's the transmittance error with respect to the perfect filter of several wavelengths. And the thing is that with this model, it's also there's a lot of interactions between the different inputs. So high interaction and high dependence here, correlation. And in this case, we only have access to an NID input-output sample of size n equals 1,000. And we use the nearest neighbor approach in order to estimate the Shapley effects in the PME. So we did an implementation in the R package sensitivity, took about 4 minutes, but parallelized on 8 cores. And the number of neighbors is arbitrarily chosen to be equal to 6. This is a whole other conversation. And these are the results. So on the left, I have the Shapley effects, and on the right, I have the PME. So the only thing that differs between the two is the aggregation process. Okay, they're based on the same estimates of the closed Sobol indices. But here on the left, what I can see is that the range of importance is actually pretty narrow. So I'm not really able to tell if I4, for instance, is that much important than I5, if I were just to focus on the left graph. But here, by computing the PME, what I see is that I4 is actually very less important than I5. And this is what I meant by, in situations of highly correlated inputs, the Shapley effects are going to tend to give the same importance to everyone, but the PME are going to be a bit more discriminative. Keep in mind that here, the importance order between the inputs is the same, but it's not always the case. The PME can have another importance order. And so here, we tried to build a surrogate model to approximate this real true model. And we used the Gaussian process. And so by using the whole data set, we had a Q squared, this is the R squared of the Gaussian process computed on the leave one out scheme of 99.49%. So this is a great model. So it's a great surrogate, at least. And we wanted to perform some feature selection by removing some of the inputs, by putting a threshold of importance, which is great because in an applied setting, it has more sense. It makes more sense by saying, yeah, so I'm going to put a 2.5% importance threshold, and then I'm going to remove all the inputs that are below this importance threshold. It's a bit more interpretable when you're talking with like the policymakers or people that are not into like that are not familiar with like feature selection methods in statistics. So with the 2.5% importance threshold, I don't remove any features with respect to the importance of the Shapley effects. But with the PME, I remove two of them, I1 and I3. And I still have a Q squared, which is really great. And with the second threshold, it's 5% importance. And here, I still do not remove any feature with the Shapley effects. But with the PME, I remove more than half of the features, and I still gather almost 99% of Q squared. So in a sense, the PME, they still maintain this idea of what's important, which inputs are important, even though it's not the same aggregation process. So a partial conclusion, what we saw up until here. The Sobol indices, they're amazing. And they allow to assess the importance of inputs of a black box model. Whenever the inputs are dependent, there are two issues. The first one is that they can be negative, which hurts their interpretation, is that their intrinsic interpretation does not hold. This comes from the fact that Hovding's decomposition does not hold. And a solution to the first issue is to use allocation, so aggregation of these Sobol indices from cooperative game theory. For instance, the Shapley effects, which are based on egalitarian aggregations, which is the Shapley values. But there's also a lot of allocations in the literature, and many of them can be really useful for importance quantification. So yeah, a large variety of allocations can be understood as aggregation of the Arsani dividends. And in the context of GSA, these Arsani dividends are actually the Sobol indices computed with dependent inputs. And we just aggregate them. And to detect exogenous inputs, we can use the proportional marginal effects on top of the Shapley values, of the Shapley effects, to have a better understanding on how what's like the inner behavior of the model under uncertainty. The question is, what about the second issue? Here, Hovding's decomposition does not hold. So my Sobol indices, they mean something that I'm not fully able to comprehend. And this solution, even though it solves the problem of having positive indices, it doesn't solve the second problem, which is it's an aggregation of something that I do not truly understand. So in a way, it's like a band-aid that I'm putting as a solution. It's a great solution. And in practice, it works really, really surprisingly well, because it still gives, it still manages to, as we've seen in the previous example, it still manages to catch the importance of inputs. But it's a bit tricky. We want to be able to actually have a nice result that states, yeah, this is how we can perform importance quantification with dependent inputs. And the key of the meaning of the Sobol indices is actually Hovding's decomposition. And naturally, what we want to do is to generalize it to dependent inputs. And we are by no means the first ones to have tried to tackle this problem. There's a lot of people throughout the years that worked on trying to generalize Hovding's decomposition to dependent inputs. But we believe that we found an interesting approach on how to tackle it, and with a kind of a geometric interpretation. We will see that it's really geometric, actually. So it kind of makes sense in a way. And it's under a really, well, we'll see. So in general, mutual independence is actually pretty restrictive. This is a really complicated thing, because it's much more restrictive than checking if my inputs are pairwise independent. Like they can be pairwise independent, but not be mutually independent, because I need to check all the subsets of inputs must be independent with one another. And the first challenge was to try to define a situation of non-mutual independence. And we actually achieved to do this by imposing two assumptions. I'm not going to go into the detail. The first one, we called it the non-perfect functional dependence between the inputs. Basically, what it states is that I can't be able to express my inputs as a possibly nonlinear function of other inputs. For instance, I can't be able to write x1 as being a function of x3, for instance, but not necessarily linear. It can be non-linear function of x3. And the second one is a non-degenerate stochastic dependence between the inputs. And this one is a bit more tricky to understand, but it deals with trying to compute correlations, but correlations in a really abstract space. And what we're saying is basically the correlation must not be equal to 1, but in this abstract space. So it's the same idea as saying that, yeah, my inputs are degenerate if I have a correlation of exactly equal to 1 between two of them. It means that there's some functional dependence between them. But here, these are two separate assumptions. So there's a functional dependence and a stochastic dependence. And under these two assumptions, what we can do is decompose the space of outputs, in a sense. So quickly, this is the Hilbert space of functions of x. And under these two assumptions, we can actually show that any real-valued random output with finite second moment, which is the same thing as Hoeffding's decomposition, can be uniquely decomposed as a sum of representants. And here, my representants are going to be hierarchically orthogonal. Some of them are going to have a covariance between them, but not all of them. And this is opposed to the pairwise orthogonal condition that I had with the Hoeffding's classical result. And we can also characterize them, as we did with Hoeffding's decomposition, not using conditional expectations, but by using these weird oblique projections, which I'm calling them M of A. And these projections, so you can think of them as not projecting straight, but projecting in some weird direction. And the direction is actually going to change with respect to the dependent structure. And the nice thing is that in our setting, if the inputs are mutually dependent, actually these weird projections are equal to the conditional expectations, which are just orthogonal projections. So in a sense, we actually recover Hoeffding's classical decomposition. The only thing that changes is that I'm not projecting in the same way. There's no, yeah, there's a typo here. Forget the given xb. It's just the mb of g of x. So a quick illustration to see here. This is a setting where I have a bivariate function. Okay, so hierarchically orthogonal, it states that g of 1, 2, my pure interaction, my bivariate interaction, is going to be orthogonal to the pure individual interaction, in a sense, of 1 and of 2 as well. So here, my model G, I'm actually projecting it orthogonally into this space. And here, I can recover G1, my representant, by projecting with the same angle between the space V1 and V2. Because the dependence, what it's going to do is that it's going to introduce some angle between those two spaces. But if I were to project orthogonally, I wouldn't end up in the same spot. And usually, the oblique projections, they differ from the orthogonal projections. So here, these are not the conditional expectations and my projections MA. These are other projections that I need, but I need them to build these projections MA. So now, knowing that, we can talk about variance decomposition. So what we proposed are actually two complementary approaches for decomposing the variance of g of x based on this generalized decomposition. And they're really heavily inspired from the existing literature. The first one, we called it the organic variance decomposition, which aims to separate pure interaction effects to effects that are just due to the dependence. And in this case, we can use them if the dependent structure of X is unwanted. I don't want really to include it in my study because I'm really focusing on what does the model do? What are the interaction induced by the model? And beside that, what are the effects of the dependence? I want to separate them. And the second one is we called it the orthocanonical variance decomposition. And in the case where the probabilistic modeling of X, having dependence between the inputs is actually inherent to the uncertainty modeling. And so we want the dependence to be part of the study. And it amounts to quantify some structural and correlative effects. So the first one, I think that Thierry Mara is going to like this slide because this is actually what your paper did, is that the notion of pure interaction, it's intrinsically linked with the notion of mutual independence, because pure interaction only makes sense when you're mutually independent. And the idea is to be able to transform my dependent input into a mutually independent version of them. So basically I have the same margins, the same marginal laws, but they become mutually independent. So I need to find some transformation to take them as dependent and transform them to being mutually independent. And in this case, I can compute the Sobol indices for my mutually independent version of dependent inputs. And this is what we called pure interaction. And this is actually, it strongly resembles the independent Sobol indices proposed by Thierry Mara. And actually, in some settings, whenever the inputs are Gaussian, for instance, we know how to transform them to go from a dependent state to an independent state. And we can also then with elliptic distribution, and this is the work of Lebrun and Dutoit. And to define the dependence effects, so now I know the pure interactions of my model. But to define the dependence effect, we've seen that the orthogonal projections and the oblique projections are not the same, but actually they are the same if and only if my inputs are mutually independent. So we can leverage this by basically computing the distance between the orthogonal and the oblique projection. And what's nice about these indices, they're positive, but under my two assumptions, if they are all equal to 0, then it's equivalent to x being mutually independent. So if x is mutually independent, my dependence effects are all equal to 0. If they're not, there's an effect due to the dependent structure. And the question is, why do they sum up to? I have no idea, but probably it's going to be some sort of overall effect of the effect of the dependence on the model's uncertainty. Now, the second part, so this is if the dependence was unwanted in the modeling process. But here, my dependence is inherent in my modeling. So in this case, we can leverage the covariance decomposition proposed by Hart and Grimaud by stating the first indices are going to be the structural effects. They're just going to be the variance of my new representants in my new decomposition. And if the inputs are mutually independent, these are just the Sobol, pretty much the Sobol indices. But also, I'm going to have the correlative effects. And this is due to the fact that my representants are hierarchically orthogonal. So some of them have a covariance. And I'm actually going to compute the covariance of my represented GA of XA with all the other representants. And this is going to be the correlative, what we call the correlative effect. And they have a nice interpretation in the sense that the pure interaction effects, it actually amounts to finding a transformation in order to straighten the space for these two spaces to be orthogonal. And I'm just computing this distance, the orange distance here. If it's big, then G1 have a big effect. And here on the right, this is if my dependence is wanted, the blue ones are going to be the structural effects. The correlative effects are going to be a function of this lambda here, of the angle between the subspaces. And the green quantity here are actually my dependence effects. So pure interaction with dependent effects. So the difference between the two projections. And then I have something that deals with the distance to the origin of G1 and of the representance and alpha as well. And maybe, I don't know for sure, because this is really preliminary work. We did the math, but now we need to go a bit beyond. These are a good candidate to solve our second issue. So now, some perspective. The main challenge is estimating the oblique projections from observations. They look a lot like conditional expectations, but actually we haven't found an off-the-shelf method to estimate them. So this is just a theoretical construct. And we're missing something to make it like truly useful in practice. But we're working on it. There can be a lot of applications to influence quantification. For instance, global, when we're dealing with the variance, or local, when we're dealing with an evaluation of a model, sensitivity analysis, going towards theoretically grounded explainable AI, but also fairness assessment. If maybe my model is subject to some protected input, I can be able to assess if this protected input actually has an effect on my model, which is really, really wanted and really nice to have if I want to maybe one day certify that a model is fair. It doesn't discriminate, for instance, between two different groups of people. And the last perspective is to go beyond hierarchical orthogonality. There's a really nice paper, which is really recent, where they used another condition, which they called stacked orthogonality. And it's not the same as hierarchical orthogonality. And they were able to find the decomposition of the model, not the random output as well. So here are a few references, and I thank you for your attention. And if you have any question, I would be glad to try to answer them.
Wow, Marouane, thank you so much. It's been a pleasure listening. I actually came here thinking that I wouldn't understand anything, but I not only understood the new stuff, more or less, I also learned new things about the old stuff. So it's like very grateful to you. And I love the geometric view of the or geometric attempt of the aligning interactions and dependencies. It reminds me of vacuum being a field with, or a model with independent inputs, and then interacting or not, and then putting that model into actually gravitational field. It's like representing some dependencies into the system. And the question is about how you kind of straighten that new system of coordinates into the new one. Yes, exactly. Wow, I have millions of questions, and actually I want to request the data from the optical filter model just to play around and see how it works. And I want to play separately with a small model with exogenous input, correlated input. But I'm sure that a lot of people also here have questions or comments. Please go ahead. I can wait. Andrea.
Why exactly you use the term hierarchical to define the independence?
Okay, I use the term hierarchical to define the now. Okay, I'll try to give you an answer without going maybe too much into the detail. But the thing is that to find this decomposition, what we actually did was take the L2, the Lebesgue space of functions of x. And what we did is that we said we want to decompose the space itself, not the functions, but the element of the space as a direct sum decomposition. Why do we want a direct sum decomposition? It's because it gives a unique sum of elements of the subspaces involved in the direct sum decomposition. But we had to impose a condition to build the spaces themselves where the representants live. And this condition is hierarchical orthogonality, meaning that the space of interactions of x1, I'm saying it's weird to say interactions of x1, but the main effect x1, all the functions of x1 must be orthogonal to the function, the bivariate function of x1 and x2. So here, g of 1 is going to be orthogonal, no correlation with g of 1, 2. And we keep going. G of 1, 2 will have no correlation with g of 1, 2, 3.
1, 2, 3. Okay, okay.
Yeah, exactly.
Yeah, clear.
And this is a choice. We can do something else as well. So this is why one of the perspective was to go beyond this hierarchical orthogonality condition.
Thank you.
May I?
Yes,
Sure.
please go ahead,
Yeah,
Thierry.
sure. So thank you, Maran, for your presentation. Very, very interesting. Reminds me some stuff that I've worked on and some also questions, but I am trying also to answer. To come back to this hierarchical orthogonal approach, I think it's related to the work of Tim Bedford in 1999.
Yeah.
Who have proposed this kind of approach to obtain decomposition of functions of increasing dimensionality, which are orthogonal.
Yeah.
But the problem that he faced was in the interpretation of the results, because you change the functions in such a way that they are orthogonal to each other, but then you realize that he could not say, okay, but the contribution of that functions is purely due to this variable. Do you see what I mean?
Yeah. Yes.
Okay, so he gave up. I mean, he didn't go ahead on these techniques. On the other hand, and I think you mentioned it in your presentation, instead of orthogonalizing the functions, which of course it's a matter of choice because it's not unique in the sense that, okay, you can decide in which order you orthogonize the functions, but so that's why for me it's a little bit weird to see uniquely, because it's not unique. Actually, you can.
Yeah,
it depends on how you rank.
The unique decomposition is the sum, but you can find many unique decompositions.
Yeah, which are orthogonal. Exactly.
Yeah.
No? Yeah. But on the other hand, that's why in 2012 I had the idea, thanks to a work of another guy called Gärtner, an American researcher, to instead of orthogonalizing the functions in the decomposition in an hierarchical way, okay, we have decided with Stefano to do it. To orthogonalize, actually to independentize the input variables. Because by doing so, you have some kind of interpretation of the sensitivity analysis, okay? And this is done with the Rosenblatt transformation, right? That's how we tackle this issue in order to be able to identify variables that are independent, are important because they are correlated to the other variables, or if they are dependent because there are some kind of structural relationship between the input and the output, right? So that's the other way around. I think it's not that easy to address the issue by orthogonalizing the functionals, but maybe.
And I had an idea that I want to share with you. Is that the idea was we can see the choice of this structure as a free parameter. And an idea that I have, I don't know, maybe it's completely far-fetched, but the idea is to find the way for this correlative, basically finding the unique decomposition such that the correlative effects are equal to 0. Not because they are non-correlated, but because basically you straighten, you make the space non-orthogonal above it to compensate for the angle alpha here. And this is just a far-fetched idea, but I'm pretty sure you can actually define some sort of structure which is not going to be hierarchical orthogonality. It's going to be different, but it's going to compensate with the other ones, which would end up in different representants, but without any correlative effects. So you can just look at the structural effects. And studying these representants may be really interesting. This was another idea I have, but yeah, I completely agree with you. You can look at it as a free parameter, and the overall interpretation is going to change with respect to choosing another orthogonality structure, or even not orthogonality, but some. But the nice thing, I haven't talked about it in this slide, is that it amounts to trying to find complements of subspaces. So this is actually a really how can I say that? This is really like from the field of functional analysis. This is just by stating, yeah, I need a complement, and I'm going to take the orthogonal complement, but there are other complements. And it becomes clear that it's some sort of free parameter. It's just an arbitrary choice to take the orthogonal complement, which ends up as being a hierarchical orthogonality at the end in the construction of the proof of the decomposition.
Okay. Regarding what you have shown just previously, this how you call it, structural sensitivity indices, let's say, and correlative effects, right? These things are related to the work of rabbits, right?
Yeah,
this is how rabbits.
Right?
These are the definitions of rabbits. Okay, to compute this sensitivity indices. I was wondering. Okay, just to let you know, I'm also working currently on this. On the Shapley effect. No, Shapley effects in general. Okay, I have a project working with another colleagues of mine. We are working in the field of climate, let's say, air pollution. Let's say, due to forest fire, forest. And we use data, and we try to understand in the data whether we can explain it with some data that we observed, but is related to the fire, and to try to find a link between some other variables that we have measured. Okay, so there are no models between, and we try to find out whether there are some relationships, okay, in terms of Shapley effects. This is how we do it, because we have correlations with the dependencies in the data set, and we also facing the same issue. Okay, I'm using different techniques, but this is more or less the same idea, trying to see whether an input is important because it is correlated, only because it is correlated to the others, or is it also correlated because there may be some part of the signal that we are interested in, which is only due to these variables and not to the other one. You see, so I'm thinking in terms of signal processing at some harms, because there may not have. I mean, you may have correlations, but not causality between variables. You see what I mean? Why it's challenging, because you don't have a model in between. You just have the data. So congratulations for your work. Very,
thank you very much.
Impressive, and keep on working on it. And maybe we can one day you keep in touch and try to figure out how to.
Well, sure, of
tackle
course.
different. I will be pleased. So feel free.
I see, congratulations, exactly. I also think it's very interesting because especially what you mentioned in the very last slide, the issue of interpretability and fairness, and the idea that you can use this to check for protected attribute. I could imagine that if you are successful in your investigation, your approach would be demanded by regulators before a given software, artificial intelligence software is put on the market, because you would have to certify that they don't allow discovery of protected attributes. So I think there is a lot of interesting application for your stuff.
Yeah, this is the subject of my postdoc, and
Okay.
we have. Well, I've started like a month ago, so we don't have anything concluding yet, but we're really looking at it. So on the basis of actuarial sciences, because there's a lot of interesting questions. For instance, there are models that are used to give credit loans to people, and you need to be able to compute the risk of not of someone not being able to reimburse this loan, but without using these protected attributes. So
Exactly.
it can be gender,
yeah,
it can
exactly.
be age,
Not
it can
based,
be a lot of things. And using
Sure.
AI methods actually improves a lot the accuracy of predicting this risk and being able to say if I'm giving a credit to someone or not. But they can't use them because they are not able to, like, theoretically state my model doesn't use this input or is not subject to this input. And there's actually a lot of interesting things, and it looks a lot like sensitivity analysis. And there's also a lot of geometric interpretation in the field of, well, causality as well, but fairness assessment also. There's a nice paper by Clément Bénès, who showed that actually the fairness metrics can actually be related to sensitivity indices. And it's really, he proved it theoretically, and it's a really interesting papers where he makes he bridges the gap between sensitivity analysis and fairness. For instance, I think the Sobol indices have a name in the study of fairness, and it's a particular kind of fairness. I think it's demographic. I forget the name, but demographic something.
Can you share the paper then?
Yeah, sure. Of course.
Mm-hmm.
I'll put it in the chat.
Yeah, in the chat. Okay.
Yes.
And yes, maybe we also put the slides somewhere publicly available, and put the link also in the description of YouTube video.
Sure. So I'm gonna put the slides on my website, and I can send you a version of them as well. And I'll send you.
Okay.
I have a GitHub repository with the data that we used for the use case that I showed as well. That's just an input-output.
Fairness in a global sensitivity analysis. Okay, thank you. Interesting. Yeah. Okay. Thanks a lot.
No worries.
Any more question? I think Sergei might have any questions. Sorry if I'm forcing you. Sergei, you're muted. Let me. We can't hear you if you're trying to talk. Okay. Yes, please.
Yeah. So if you go to your slide 7, when you computed Sobol indices for the correlated case with normal.
Yep.
With normal. If you, well, this is, I'm a bit puzzled with this value, that if you compute the Sobol indices with what we suggested with Thierry, separately, they would not be negative. They would always be positive. I mean, I call them generalized Sobol indices, as Thierry called some of them full, some of them independent.
Yeah.
They can be equal to 0, but they would never be equal. They would never be negative. So I'm a bit puzzled why. why is that negative? Thierry, maybe you understand why is that negative?
So in this case, why are they negative? It's because it comes from the fact that when you're taking conditional expectation, this is due to the sum here being before the variance of the conditional expectation. So here it's basically this green sum. This is related to the inclusion exclusion principle, and it just states that I'm adding something, then I'm removing something to get like the intersection, basically saying that the intersection between A and B is equal to A plus B. What is it again? A plus B minus the intersection of A, B, or something like that. But you're able to, by adding and removing stuff, this is a telescopic sum. And actually, when you do the computations, so we started by computing V of E of G of X, the conditional expectation, then applying the sum, and you see that pretty much a lot of things cancel out, but at the end, for 1, 3, and 1, 2, 3, there's a negative part in front of them. And so this is when you keep if you really keep the same formula by taking this formula and computing it whenever there's dependence. Now with if we were talking about different indices, such as, for example, the total Sobol indices, or you said independent Sobol indices, you said the full as well, total, full Sobol indices. This is not going to be the same thing. So some of them may be positive as well. But the thing is that here, with computing all the Sobol indices at every order possible, for every interaction possible, you actually, usually when the inputs are mutually independent, have a complete view of how the model behaves. For instance, usually there's not a really high interactions, but if you compute all of them, if it were to happen to have high interactions, you would be able to spot them by computing all the Sobol indices. Whereas in this case, I can't conclude if it's if there's high interactions, or if it's something that is due to the dependence. And this is just a small use case.
Well, if you compute the whole set, full indices, total independence, then full independent, well, is this called, full independent, the second set?
First.
Yes.
Yeah, the first
independent, and then total independent, right? The first one, independent. Then you have the whole picture, and it's much more straightforward. And also, Shapley values will be in between. So Shapley value just give you one slice, one answer, while these indices, they give you 4 different values, and give you much more full information. So Shapley are inferior to Sobol indices if you compute all of them, and there is no problem with numerical estimation. I mean, there is some, but there is no combinatorial complexity.
Yeah, yes, I completely agree with you with the Shapley values. Well, the thing is that they are an answer, in the sense that they give one answer. They try to solve this particular problem, but they do not solve all of the problems. And this is true that by computing only the first order Sobol indices and the total Sobol indices, you can actually see, well, if there's a difference between them, you know that something is happening, and it's either due to the dependence or either due to higher order interaction. And if they happen to be the same, then you know that your model is basically a linear sum of nonlinear functions.
Exactly.
And it doesn't go, and well, the thing is, like in the papers that we wrote, and usually when working in practice, what we do is that we compute everything and we use all these elements to have a more complete picture. By keeping in mind that the Shapley effects are just an aggregation. Saying it's like a mean. It's a mean behavior. It doesn't go like you can't go too finely into the details. And actually, you can see the second part of the talk with the generalized Hovding decomposition as an attempt to being even more precise. By saying, okay, now if I'm in a case of the first order Sobol indices and the total Sobol indices are different, the question is why? Is it really due to the dependence? Is it really due to higher order interaction? And trying to understand why, how this gap, why is there this gap, basically. So these approaches are complementary in a sense, and everything gives you some idea of some aspects. And it's great, but it's not an all-in-one tool, especially for the cooperative game theory, since they're just an aggregation of what's of the information contained in the Sobol indices here.
Marianne, could I add here, if I may interrupt? It feels to me, I've never worked with Shapley values, but it feels that it's really convenient method to do feature selection, for example, because all your indices are positive, right? And depending on which aggregation you use, it's like helps you to do it one way or another, which you were showing. But then with Sobol indices, I actually personally prefer to have in front of me not the first and total indices, but first order indices and second order indices, and then closed indices, which you can also compute from the first two or then three or whatever is the order of the model. So, and then, for example, if you have two inputs which have very high first order effect, but then very highly negative second order effect, which means that they're correlated and kind of they have overlapping information on top of their first order effects. It's actually a very interesting insight for policy making, because you know that you can use either or, but you don't need to use both of them, because second would kind of adjust itself. So you need to choose which one it's easier for you to adjust, something like that.
That's a great take. It's true.
You mentioned that instead of orthogonality, there could be something that might take away the angle between interaction correlation in the geometry. I was thinking, I'm not a mathematician, so probably I'm saying nonsense, but the idea is that what if orthogonality is like, it's orthogonal on the, it has an angle in Euclidean space, but if you take non-Euclidean space, like for example, something elliptic, right, where parallel lines actually intersect, then maybe you actually get to your angle and you will manage to get correlated cases orthogonal by itself, just on curved space somehow. And that thought is coming from my experiments of trying to find kind of relationship between interacted and correlated inputs with different degree of correlation. And it actually, the two lines look, one line with non-dependent inputs looks, one line with no interaction looks straight, and another one is more like elliptic around it. And in the case of no interaction, in the case of no correlation, the distance between the two is exactly the interaction. And then it gets reduced by the correlation. So interaction is reduced by the correlation, but I'm not in the way anyhow able to express that mathematically. Yes.
But this is actually a great take, because here, let me check because I don't see the. Yes, I've put an asterisk because this is actually not a Euclidean space. This is just an illustration, because here V1 is an infinite dimensional Hilbert space. and V2 as well, and V12 also, and the sum of the three is also the big Hilbert space, basically. So it's really, really abstract. This is a really abstract construct where here the norms are defined with respect to the measure, which can be written with respect to the law of X, but not necessarily. And in this case, I'm putting the projection as something simple here. But the thing is, this is why we're not able to estimate it. It's because it's a projection from an infinite dimensional Hilbert space onto another infinite dimensional space, being parallel to a third infinite dimensional space. And this is why it's a bit tricky in theory to get it to work. It's not like this example is really a linear case, but it's not linear at all. I don't even know if this plane is straight or if there's a curve or it's weird. I have really no idea. I'm not an expert in geometry as well. And but this is really interesting to be able to actually define and characterize these by saying, yeah, you need to look at the oblique projection, which can theoretically be well defined, but now it gives us a goal in a sense by saying, oh, maybe this is what we're interested in, so we're gonna put some effort into trying to estimate them, even though it's complicated. But we have these theoretical arguments to prove, to convince us at least, that these are interesting to look at. And it's much more motivating because if someday, as Andrea said, if I'm in front of a policymaker, I can tell him, these are my indices and these are the pages of mathematics and proof that states that they're interesting. And not by saying, yeah, look at it from an example perspective, just an example perspective. But the three of them need to line up. Like you need to have the theory, the practice, the examples, and then a way to be able to compute them. And this is really because we're talking about critical systems. Maybe in reality it's not that, but that's the mental image that I have in my head, that in order to convince policymakers or the regulation authorities, I need to give the full picture and understand everything, and that everything needs to be laid out and understood and studied and stuff.
Yes, makes sense. Speaking of aligning theory and practice, I have an intuition. I'll have to check. I'll do it immediately tomorrow. I'm super curious. I have an intuition that the method, the estimator for Sobol indices that Sergei calls double loop reordering, I call simple binning approach, which is simply binning the space, evaluating the expectations, and taking the variance of them as conditional. Very simple approach. It feels to me that even with the classic aggregation as in closed indices, that would capture the external variables, even if they're correlated with the model one. And at least the one that you showed, I have to check it numerically, but at least the model you showed, x1 plus x2, I have a feeling that x3 there will have the first order effect of positive value equal to the negative value of the second order effect with x2. And so its closed index would be equal to 0, which is a manifestation of an external variable, or Shapley effect would be equal to 0, right? If that's
no, Shapley would not be 0.
okay. Okay.
I think.
So Shapley would not be 0, but
yes. Okay.
PME
Sorry,
Shapley.
I don't know. I'm not.
No,
I haven't
Shapley,
been working with them, but I have a feeling.
But what you say, yes, what you say could be the case.
Yes,
yeah.
I will do some tests tomorrow. It's very interesting to see. But that means that practical numerical method actually unifies your proportional marginal effects and the classic allocation for the closed indices somehow. No idea how.
Yeah. The thing is, with the proportional marginal effects, we're actually looking at the total Sobol indices, but at every possible order. So if you take, I know it was Bertrand who told me one day, because I was talking about high order total indices. What are you talking about? Total indices are just the first order, but you can actually define them as higher order. And it has
Yes,
a
of course,
meaning
depends
in
on which
composite game
orders
theory.
of interactions they include, right? Yes.
Exactly.
Yes.
And the thing is that this proposition, so the proportional marginal effects rely on the behavior of the total Sobol indices at every possible order. And the exogeneity detection actually relies on the fact that you need to have, so this is a weird one, but you need to have your total indices, every total indices that involves, for example, x3 must be equal to 0. And this happens, so this, yeah. So you need to check all of them that involves x3, and they must be equal to 0. And then you can conclude that xi is x3 is exogenous. And
But
with
this
the
is
mild
what you call the
assumptions
degenerate.
here,
Isn't this what you
Yeah.
call the degenerate case?
exactly. And with the mild assumptions, it amounts to just checking the first order total indices of x3. And we figured that while writing this paper, we figured it out. And this is what is behind the PME, this exogeneity detection. And the thing is that the Shapley effects do not rely on the same thing. So here there are two different ways to compute importance. And this one doesn't rely, well, it can't be equal, it can be not equal to 0 if the total Sobol, the first order total Sobol index is equal to 0. Whereas this one is necessarily equal to 0 if the total Sobol index is equal to 0. And this is why we have this equivalent. And it's just the aggregation thing, like checking in the aggregation. Basically, it's just like you can see it as an if then else statement. If the first total order is equal to 0, then the PME is equal to 0. But if it's not, then you can do a whole bunch of things and aggregate them differently. But yeah, if you're really interested in just looking at exogenous inputs, compute the total indices. It's enough. And if it's equal to 0, then you're good.
Yeah.
Yeah. Any more questions to
Yeah,
Marian?
just maybe one
Go
thing I
ahead.
would like to add. When you said the total indices, you mean the total indices like Sergei defined it, right?
Yeah.
And this is what I called the independent total Sobol indices, because you have another kind of total which takes into account both correlations and dependencies. So that's why I have I distinguish with two, kind of sensitivity indices. And maybe that's why people sometimes they are puzzled by this total indices, because it can be smaller than the first order, right?
Yeah.
In the case of dependent variables. So I think it's maybe better to say that it is the independent total order indices, just to say, okay, there is something missing, independent.
Yeah.
So, okay, I didn't take into account correlations. Right? But I agree with you. This is one way this is the way actually I use to know whether a variable is exogenous or not, right? Usually. Yeah.
Maria, are you uploading the registration?
Registration?
The
What do you
recording
mean?
of this?
Yes, the recording of it I want to upload to YouTube.
Okay, thank you.
Yes. Yes.
Send us
It's
a note
super
when you
interesting.
upload. I would like to share it with Julia, one of my
Absolutely.
co-author. Yeah, okay.
Absolutely. Super interesting presentation.
Thank you very much. And I'll send you the slides and I'll put them on my website as well. I haven't said it, but there's a bunch of papers that we've written during my PhD. They're all also available on my website. Just firstname, lastname.com.
Yes.
But I send the link to you, and so
Yes, it's also first
you.
link that comes in the Google search when your name is Google.
Oh, really?
Yes,
Nice.
yes.
Must have a nice page rank. I haven't paid Google for it to be first.
Yes. Okay, if no more questions, we anyway stay in touch. There are emails, there is Discord channel, and yes, thank you, Marianne, for this brilliant presentation. It was a pleasure personally, and I think everybody else enjoyed it.
Thank you very much.
Thank you.
Thank you, Marwan. Thank you, Maria, for organizing.
Thank you.
Yes,
Thank you,
my pleasure.
Maria.
Thank you again,
Thank you,
Maria.
Marwan, and everyone.
Thank you.
Thank
Bye-bye.
you.
Bye-bye.
Bye.
Bye.